it goes to 0. When you evaluate at t is equal to 0, the exponent becomes 1. So it's this value minus this value. And then I only have the bottom value left. And the answer is 1 over a plus j omega. Okay? So, we know one thing for sure, that e to the minus at u of t Fourier transform to 1 over a plus j omega. Okay? And I'm going to show you a trick on how to find the Fourier transform of t e to the minus at u of t. Okay? How do I find this Fourier transform? You notice that this thing here is just dA, differentiating this with respect to a of this function and putting a minus sign in front. If I differentiate this function with respect to a, I get that function. Okay? But this function itself can be written in terms of a Fourier transform by the Fourier transform theorem, that this is equal to 1 over 2 pi minus infinity e to the j omega t here, and then the Fourier transform of this quantity, which is given to be 1 over a plus j omega. This equals that. We have proven that to be a fact. Okay. Now if I differentiate this equation with respect to a, I can differentiate the left-hand side with respect to a with a minus sign. I will get this left-hand side. Okay, so I can put the whole equation under the derivative operation, dA. On the left-hand side, I will get t e to the minus at u of t. What do I get on the right-hand side if I were to differentiate the right-hand side with respect to a? I can take the derivative operator into the integrand, because that is allowed. It's a linear operation. Derivative, the sum is the sum of the derivatives. Okay, integration is just sum of terms. So if I have a differentiation outside of the sum of things, I can take the derivative inside, and it's the same as the sum of differentiation. So I can take the derivative operator all the way in here. Does that make sense? Okay. Larry thinks that it makes sense. Does it make sense to everybody else? Okay, Georgie thinks that it makes sense. What is that? Right, I can. Derivative is a linear operation. So derivative, essentially derivative of two functions is the sum of the derivative of the individual terms. Is a linear operation. Okay, derivative, let me draw this line over here. Derivative is linear operation. If I take a derivative of sums of things, it's the same as the sum of the derivative of things. Okay, so I can take the derivative inside and differentiate the integrand. And then if I do that, if I differentiate the integrand with respect to a, only this term depends on a. What would I get? I get 1 over a plus j omega squared for the right-hand side. Does everybody agree? If I take the minus the derivative of this term with respect to a, I get that. Which means that the Fourier transform of this must be equal to that. Okay, so I arrive at a new identity for you. Yes? Yeah, but I have a minus sign here. Okay, I differentiate this, I get a minus sign, but it cancels with that minus sign over there. So I have this identity that t e to the minus at ut Fourier transform to 1 over a plus j omega squared. Okay? So, now I can use this identity to look at the output response of a linear system. Okay, for example 2.5, the LTI system has h of omega equals to 1 over 1 plus j of omega. And then it has an input. The input f of t is given to be this quantity over here. Okay, with a equals 1 actually, it's actually this quantity over here. With a equals 1, so f of omega, if I have an ft coming in here, f of omega is actually equal to 1 over 1 plus j omega, because a equals 1 over here. If I use this identity, okay, I use this identity which I derived over here. I derived the identity over here. That f of omega equals that. Then what is y of omega? If this is y of t coming out here, y of omega should be equal to what? H omega times f of omega. So it is 1 over 1 plus j omega squared. Okay, because if you multiply these two quantities together, you get that quantity. Okay? Now, you use this as your identity. If you have something like this, the Fourier inverse transform to that quantity over there. So if I use this formula, I say that my t must be something with a equals to 1. Okay, set a equals to 1, in this formula I get this identity. Y of t looks something like that. So what it says is that if I have an input, if the input looks something like this, okay, in this case the input f of t looks something like this, 0 decay. Okay, that's what this input is, with the value of 1 over here. And then the output, okay, y of t will be given by this formula, so it looks something like this. Okay, if you plot this, it's 0 when t is equal to 0. It grows a little bit when t increases, but then it exponentially decays after a while. And they are all 0 for t less than 0. Okay, are there any questions on this derivation? Okay. No questions, then we can move on and go to the next example.
I have a question.
Yes, yes.
So why did it become 1 over a plus j omega squared, like in the integral down over there, like when?
Oh, I'm saying that if I had the left-hand side, I can write the left-hand side as the derivative of this.
Yeah.
Okay? And so the left-hand side can be written as that. But I have an identity that I have established over here, which is that without the derivative, okay, without the derivative, this must be equal to that by the Fourier transform theorem. Okay? Now I want to get the left-hand side to look something like that, so I apply this derivative operator to the left-hand side. I will get something that looks like that. But I need to apply this derivative operator both on the left and the right-hand side. When I apply on the right-hand side, I use the fact that derivative is a linear operator, derivative of sums is the sums of derivatives. Integration is just a sum. Okay, if I differentiate sums, is sums of the differentiation. So I can take the derivative operator inside and differentiate each term one by one for all different omega. Okay, because I'm summing this thing over all different omegas. When I differentiate each of these terms, I get that quantity over. Okay, so this is just equal to minus dDA of 1 over a plus j omega. That's what I mean. Okay. Okay, you get it? Everybody gets it? Okay, good, wonderful. So let's see. Let's do example 715 then. Oh, this is example 715. Let's do example 716. Then I'd like to introduce the concept of the zero state response. Okay, the concept of zero state response means no input at t equal to minus infinity. If you have a system and there's no input to it, at t equals minus infinity, which is the beginning of time, okay, like this system over here, okay, there's nothing before. Going to t equal to minus infinity, there's nothing there. And then at t is equal to 0, I turn on the input. Okay, so there's nothing or no state before. This is called a zero state response. Okay, you were set to zero state initially. This is also called a zero state response in the textbook. Okay, just one important concept before I move on. Let me go and do example 716 then. Example 716, the input is given to be the sinc function. Okay, the sinc function. What is the Fourier transform of a sinc function? What is that? It's a rect function, right? It's a rect function. So this thing Fourier transform to f of omega equal to pi, the rect function, omega over 2. Okay, you can look up in your table. And then this also has been derived in section 7.1. If you read your section 7.1 carefully, this formula has been derived. Okay? And then you're given the fact that h of omega is a rect function of omega. Okay, so h of omega will look something like this. H of omega, omega equals to plus half, omega equals to minus half. Outside it is 0, and inside it is 1. That is what the rect function looks like. Okay, that's how h of omega looks like. And then if you have a linear time invariant system described as such, okay, and you have an output y of t, what is the Fourier transform of the output? It will be f times h. Okay, f times h, and if you multiply f and h together, f is given by this, h is given by that, so you get pi rect of omega over 2 times rect of, let me erase this so that I can write something here, omega, okay? So, but if you were to plot f of omega, how does it look like? F of omega, when would it become 0? What would omega be? Omega over 2 has to be half. So omega must be 1. Okay, so it would look something like this. Omega equals to 1, omega equals to minus 1, then it goes to 0. But what would its value here be? Pi. Okay, so when you actually make the argument be divided by 2, you actually stretch the function and make it wider. Remember that. Okay, when you divide the argument by 2, you make the function wider, twice as wide as this one. Okay, so when you multiply this function together with that function, which one takes over? The narrow one takes over, right? The narrow one. Both of these have value of 1 at the peak. So finally it just becomes the rect of the narrower function, which is this one. Okay? Do you agree with that? So now if you look at y of t, what is y of t? You just Fourier inverse transform this. And you can actually do a table lookup or just use this formula. Or there are many formulas in the textbook in that table 7.2 or something like that. Okay? And then you will get y of omega to be, let me see, I have this over here. Y of t to be equal to half sinc of t over 2. Okay, half sinc of t over 2. If the sinc Fourier transform to this, and if you make omega over 2, it Fourier transforms to that. That is the scaling law. I think the scaling law is not in your table, unfortunately. The scaling law in Fourier transform is not one of the properties that you have in table 7.2 or something, 7.17.2. But it can be derived very easily. Okay, what the scaling property is. Say if I have a function f of t, and if it's related to its Fourier transform by this identity, okay? If I were to change its argument, get a new function gt which is f of at. In that case, a was some other thing, like change it by half or something. Okay, what should its Fourier transform be? Okay, then I can use back this equation. This is just a mathematical identity. I can use back this equation and claim that this is equal to j omega at f of omega. Agree? That is just equal to that. Then I'm going to do a trick. I'm going to call this a new dummy variable omega prime. Omega prime is equal to omega times a. Okay? And then I'm going to write this in terms of omega prime. F of omega prime divided by a. Okay? And then d omega, I can going to write it in terms of the dummy variable d omega prime, okay, divided by 1 over a. Must be equal to d omega. So I'm going to make 3 changes, one in the exponent, one in the argument, and one in the omega. And then this new integral will look something like 1 over a times 1 over 2 pi. I take this 1 over a outside. The limit of integration is still minus infinity to infinity. Then in the exponent, I will have j omega prime t. And then I will have f of omega prime over a. Okay, so what it says is that if you change a function by changing its argument, then the Fourier transform of the new function is equal to 1 over a f of omega prime over a. Okay, that is the scaling law.
So
okay, that's why you get the factor of half.
It should be 2 sinc of 2t, right?
What?
It should be 2 sinc of 2t, right? Because it's omega by 2, so a is 2.
I'm going in the reverse direction though when I did that.
Yeah, so f of omega.
Did I have a derivation error?
No, that is correct. That is correct.
Derivation here is correct, right?
Yeah, so a is equal to 2, right?
Is a equals 2?
Yeah.
A is 1/2.
I'm going from here to here. Okay?
Yeah.
Originally it was this function. I know its Fourier transform to be this.
Yeah.
Okay? I'm going to make this into 2 times the previous argument, then I should divide by 2. Okay? If it applied correctly, this formula should work. This should be g omega prime, sorry. G omega prime. Omega prime is a dummy variable. Okay, this is called a scaling law. And you can also derive it directly. You can also prove that the Fourier transform of this is that directly also as is done in the example in the textbook. Okay, are there any questions regarding this? Okay. So I guess the thing is that let's do it more carefully. If f of at Fourier transform to f of omega, what it says is no, sorry, f of t Fourier transform to f of omega, f of at, which is this new function, will Fourier transform to 1 over a f of omega over a. That's what it says. This is the scaling law. Okay? So if you apply this scaling law to this thing, the f of omega is pi rect of omega over 2. Okay? And I want to make this to look like this thing. I want it to make this to look like that thing over there. Okay, I want it to look like pi rect of omega. So if I started out with that, I should have a being equal to 2, right? A being equal to omega over 2 divided by 2 divided by half, so times 2. Okay, so going from here to here, I need a equal to half. Right?
Yeah, then it's right.
If I take a equal to half, I can go from here to here. But then this means that the Fourier transform of omega over a is equal to a f of at. Okay, if this is true, this is true. Okay, so if this is true, then it says that this thing must Fourier transform to half sinc of half t, must Fourier transform to pi rect of omega. Okay, if the scaling law is correct. Okay. So I will skip example 7.17. I think it's quite straightforward. It's just the example of a band pass filter and a low pass filter and the kind of thing. So I don't think you would get confused by that. So let me do example 7.18. Example 7.18 says that h of omega is a very simple function. Just this function over here. Okay, what does it do to an input? If you have an input f of t with Fourier transform of f of omega, and then the output is y of t with Fourier transform of y of omega, then y of omega must be equal to f of omega times h of omega, and then that should be equal to f of omega times e to the j omega t naught. So if you were to inverse Fourier transform a function with a phase factor included in it, what does it do to the function? If f of omega, if f of t is equal to 1 over 2 pi minus infinity to infinity d omega f of omega e to the j omega t, if this is true, okay, if I have a new function now, if I have a new function, y of t is 1 over 2 pi minus infinity to infinity. This new function is just f of omega times e to the j omega t naught. And then if I were to Fourier inverse transform this, I can combine these two terms together and see that this is just 1 over 2 pi minus infinity to infinity d omega f of omega e to the j omega t minus t naught. So what does this function represent? What does it represent? is just equal to, how do you express this function in terms of f, the function f? If f of t is this, what is this function? F of t minus t naught. So a phase just gives rise to a delay. A phase just gives rise to a delay. This is a delay function. Okay. If you have f of t minus t naught is just a function moved by t naught to the right hand side. Okay, so this is just a delay function. Just remember, a phase is equivalent to a delay in the time domain. A phase function in the frequency domain is the same as the delay in the time domain. That is something very useful to remember. Any questions so far? Okay, no question, then we move on to the next example. Example 7.19. Okay, that h of omega equals to 1 over 1 plus j omega. Okay, the input f of t is given by this. How do I read this function? What is its value when t is larger than 0? When t is larger than 0, how does this function look like? 0, very good. Okay, it's just the mirror image of the exponential function going the other way. So f of t will look something like this. Okay, f of t looks something like this. It decays in the negative t direction, and then because of the unit step function with the minus argument, this thing gets flipped around. Okay? And then you can find this Fourier transform very easily. Okay, you can just integrate and find f of omega. F of omega is just minus infinity to 0 d omega e to the t e to the j omega t with a minus sign there. Okay, d omega, and you integrate this. And we know how to integrate that before. We did something very similar to this before. And hence, you have the answer of 1 minus j omega. Okay. You can also use the conjugation property that if you know that f of t Fourier transform to f of omega, okay, f of minus t, what is the Fourier transform to? The complex conjugation. Okay, this is one of the conjugation properties of Fourier transform. If this Fourier transforms to that, something that is reverse time, where you change t to minus t with Fourier transform to a complex conjugate quantity. Okay, you can prove this quite easily. I think I proved that before, so I wouldn't prove it anymore. Okay, I proved this conjugation property before. Okay, but it can be proven quite easily. So, if you have a linear time invariant system described by this, with this as the input, then the output y of omega would just be equal to h of omega times f of omega. Okay. And if you work that out, is 1 plus j omega, the transfer function of the frequency response, 1 minus j omega. And what do you get for this? You can actually, it's a plus b, a minus b, right? So it's 1 over a squared minus b squared, but b is imaginary. So when you square an imaginary number, it becomes the minus number again. So it's 1 plus omega squared. Okay? That's what you have. But how do you Fourier inverse transform this thing? How would I find f of y of t? This is a rather nasty thing to do, right? You can do a table lookup, but what happens if it's not in your table lookup? You give up. Don't give up. Good engineers, right? If you don't give up, you do partial fraction. Okay, try to write this in terms of A. You learn about partial fractions in high school, right? You write this in terms of partial fraction, and you know how to Fourier inverse transform each of these terms. Okay? This thing Fourier transform to that thing that we had before, looks something like this. Okay? This term Fourier transform to that thing over there. And the thing, if we work it out, A and B turns out to be half or something like that. Is it half? Yeah, A and B turns out to be half. A equals B equals half, right?
Shouldn't it be B omega plus C?
No. That will only have a quadratic term.
No, but the bottom is not linear too.
No, this is a linear in omega, linear in J omega. You learn how to partial fraction in high school, right? So if you do partial fraction and multiply, I think A is to the B equals to half. And I think that will work. Okay? And then you know how to Fourier inverse transform these terms. And then if you work this out, then y of t is actually half e to the minus t. So it will look something like this. It was the sum of this and that. With the half value at theta. Okay? So, I would do example 7.20 because it has no closed form. Okay? It was in terms of a sinc function that cannot be integrated in closed form. I will skip example 7.20 and let you read by yourself what it is. But I will do the last part of section 7.3. Okay, 7.2 or 7.3. Which is something very interesting, which is that if you have an inductor, you know that the IV relationship of an inductor is given by this equation over here. If you have I of t, and if you have B of t, B and I are related by that equation over here. What happens if I were to replace both B and I with Fourier transforms? Okay, if I write V of t being equal to 1 over 2 pi e to the minus j omega t or plus j omega t b, or let me use capital B of omega. And then I write I of t being equal to 1 over 2 pi minus infinity to infinity d omega e to the j omega t, and then I of omega. Okay? These are very much like phasors. They almost behave like phasors. What happens to the I dt? If I were to differentiate this equation, okay, differentiations of sums is the sums of differentiation. So I can take the derivative operator inside and let it operate on the only thing that depends on t, which is that thing over there. So what do you think that the Fourier transform of this would be? If I were to differentiate this term with respect to t, I get a j omega. Very good. Okay? I of omega. So very much like what you have learned in phasors before. Derivative operators just become j omega in the Fourier space. Okay? So this thing would actually Fourier transform to j omega I of omega. I of t Fourier transform to I of omega. B of t Fourier transform to B of omega. And you have this very simple relationship between this. Now, if you were to plug this to the left-hand side, this to the right-hand side, you will have this very simple relationship, which is exactly what you have seen in phasors. Okay? Exactly what you have seen in phasors. So this is like deja vu. Okay, something that you have seen before. Okay? So what happens if you have a capacitor? I, t, is going to C dV dt.
over 1 over j omega c times bt.
So this relationship in the Fourier space will become j omega c times v of omega. Agree? Just like what we've seen in phases before. Right? So the IV relationship for capacitors and inductors that you have seen simplified when you apply phasors technique also get simplified when you apply Fourier transform techniques. Okay? So you have V of omega is equal to j omega L, I of omega, you can call this the impedance, omega, and then you can have, for the capacitor, V of omega is equal to 1 over j omega c times I of omega. And then Z of omega for a capacitor is 1 over j omega c, just like what you've seen for phasors before. So there are more than one road to Rome, okay? So you can reach this very simplified equations by using phasor techniques or using Fourier transform techniques. So if I have a very complicated circuit, which would be something requiring you to solve ODEs, first and second order ODEs, say if I have a simple circuit that looks something like that, and then this is a current dependent source, say 3y of t, and then y of t is this voltage over here. Okay, and then this is 1 farad, and this is the driving source f of t. In the frequency domain,